I start with 8.3 generalizations. Here I start with the positive number a, which is greater than 0, and I now think of ln a. I also know that as far as the domain of the natural logarithmic function is concerned, the domain of the natural logarithmic function is this 0 till infinity, wherein we are not including 0. That's the domain of the natural logarithmic function. So I can easily think of a positive number a, and I can then think of ln a. Now, if I want to know what ln a is, I know that it is the power to which e has to be raised in order to get a. That means I can now write a is equal to e raised to the power ln a. I also know about this general property, which is e raised to the power r. And if I raise it to the power s, I have e raised to the power rs. Given this, if I now write a raised to the power x, I can write e raised to the power ln a raised to the power x, which can then be written as e raised to the power x ln a. And now if I want to differentiate a raised to the power x, I can differentiate e raised to the power x ln a. So if I differentiate e raised to the power x ln a with respect to x, I can have e raised to the power x ln a, and then I differentiate x ln a with respect to x, so that gives me ln a. So I use the chain rule. Basically, I have done this. I have e raised to the power g of x, wherein g of x is equal to x ln a, and I want to differentiate this. So if I differentiate this, I have e raised to the power g of x multiplied by g prime x, which is nothing but e raised to the power x ln a, and then it is ln a. I know that my y, which is equal to e raised to the power gx, that means I can write my y as a raised to the power x. So that means y is equal to a raised to the power x. That means y prime is equal to e raised to the power x ln a, and e raised to the power x ln a is nothing but a raised to the power x, as we know from here. So I can write e raised to the power, instead of e raised to the power x ln a, I write a raised to the power x, and then I multiply it by ln a. So this is a very important rule, that if my y is equal to a raised to the power x, wherein please keep this in mind that a is greater than 0, a is a positive number, then y prime is equal to a raised to the power x multiplied by ln a. So this is a rule to be remembered. In this case, if I put a is equal to 10, what does that mean? That means if I write a is equal to 10, I can have y is equal to 10 raised to the power x. So y prime would be equal to 10 raised to the power x multiplied by ln 10. If a is not equal to 10, if a is equal to e, then my y is equal to a raised to the power x, so it is e raised to the power x. So what is y prime? Y prime is equal to a raised to the power x multiplied by ln a. So here I should just write e raised to the power x, because if I write ln a, that is going to be ln e, and that is nothing but 1. Now in this case, if I recall what we have done earlier, if I write f prime 0, if I can just get back to this case, from here I know that f of x is equal to a raised to the power x. F prime x is equal to a raised to the power x multiplied by f prime 0. We know this, and now we have understood this. F of x is equal to a raised to the power x. F prime x is equal to a raised to the power x ln a. There, in this case, we have written f of x is equal to a raised to the power x. If this has a derivative at 0, then f prime 0 exists, and that means f is differentiable for every x, and my f prime x is going to be a raised to the power x f prime 0. So now I can write that f of x equal to a raised to the power x, f prime x is equal to a raised to the power x f prime 0. From this we get f prime 0 being equal to ln a. And we know what f prime 0 is, given the fact that f of x is equal to a raised to the power x. We know what f prime 0 is. F prime 0 is this: limit h tending to 0, a raised to the power h minus 1 divided by h. That is equal to f prime 0, obviously provided the limit exists. If this is something that I already know, that means I can now write this. Limit h tending to 0, a raised to the power h minus 1 by h. This is equal to ln a. And it actually means I can write a raised to the power h minus 1 by h. This tends to ln a as h tends to 0. I know f prime 0 is ln a. I know ln a is equal to this. That means I can write f prime 0 equal to limit h tending to 0, a raised to the power h minus 1 by h. In this case, now I replace a by x. If I replace a by x, what do I have? In this case, I'm replacing a by x, or in this case, I replace a by x. Obviously, given the fact that x has to be greater than 0, I can now write limit h tending to 0 instead of a raised to the power h minus 1 by h, I now write x raised to the power h minus 1 by h, which is then equal to ln a. Now I write ln x, wherein x is greater than 0. We are now going to deal with this. We take up any h greater than 0, and then we are going to define a function. We define the function gh by this. So I write gh x equal to this, and that means I write x raised to the power h minus 1 by h. Keep this in mind that I'm taking h greater than 0, and this is for all x greater than 0. Now in this case, I take the limit of this function gh of x, given that h tends to 0. H is greater than 0, but let's say h tends to 0, then what is the limit of this function? This is what I'm concerned about. So I write limit h tending to 0 ghx, and we know what this ghx is. Gh of x is, this is x raised to the power h minus 1 by h, and this is for all x greater than 0. I can write that as limit h tending to 0 x raised to the power h minus 1 by h. This I know from here, it is ln x. That means I can write that here. What does this mean? This means that ln x is bounded above by each of the functions gh of x. What does that mean? That just means that gh of x, this function, tends to ln x as h tends to 0. And we are going to understand this now. What we want to show here is that ghx tends to, so we will see that geometrically also, gh of x tends to ln x as h tends to 0. And I can also say that ln x is bounded above by each of the functions gh of x. Please keep this in mind that h is greater than 0. So just to understand this, just to show how that is possible, and we are going to take up the figure also. For that, again, let's consider for each h greater than 0, we take up this function fh of x, and we define this in this manner: gh of x minus ln x. We want to show that gh of x tends to ln x as h tends to 0. For each h greater than 0, we define a function fh of x, which is equal to gh of x minus ln x, and I can now write it this way. What is gh of x? I know it is x raised to the power h minus 1 by h minus ln x, and this function is obviously defined for x greater than 0. Now in this case, if I write fh of 1, given the fact that h is greater than 0, I put 1 instead of x. This gives me 0. ln 1 I know is 0. What does that mean? That means this is equal to 0. Also, if I write fh prime x, if I differentiate this expression with respect to x, I will have h x raised to the power h minus 1 divided by h, given that h is a constant, h is a positive number, it is greater than 0, minus 1 by x. So that can be written as x raised to the power h minus 1 minus 1 by x, which can then be written as x, and now I write this. So this is my fh prime x. And if I want to understand the sign of this function, in fact this is not a function, I mean this is the derivative. If I want to understand the sign of this derivative, I can say that this is less than 0 if 0 is less than x less than 1. So let's understand this. H is again greater than 0 if x is between 0 and 1. So obviously the denominator is going to be positive, but if it is between 0 and 1, we raise it to any power which is greater than 0, it will be between 0 and 1. And if I subtract 1 from something which is between 0 and 1, that will turn out to be negative. So numerator will be negative and the denominator will be greater than 0. That means this whole fraction is going to be less than 0. Also, I can say that it is going to be greater than 0 if x is greater than 1. So if x is greater than 1, obviously the denominator is going to be positive. If x is greater than 1, if I raise it to any power which is more than 0, and I subtract 1 from that, it is going to be positive. Please keep this in mind, x is not 1, x is greater than 1. So the numerator will turn out to be positive. The denominator is anyway positive, so the whole fraction is going to be positive. I know here that, let me write this again, that f h of 1 is 0. I know that. I can see that fh prime x is less than 0 when 0 is less than x less than 1. What does that mean? That means the function decreases when x is between 0 and 1. And at 1, the function, the value of the function is 0. What does that mean? That means the function decreases from positive values to 0 when x is between 0 and 1. I'll repeat this point. If x is between 0 and 1, fh prime x is less than 0. That just means that the function decreases when x is between 0 and 1. I know that at 1, the function takes on the value of 0. That just means the function decreases and it's a less than 0. That means there is a strictly decreasing function. That means the function decreases from positive values to 0 when x is between 0 and 1. When x is greater than 1, the function increases because fh prime x is greater than 0. At 1, the function takes on the value of 0. That means when x is greater than 1, the function increases from 0 to positive values. So the point to note here is that fhx, it decreases from positive values. In fact, I should write it decreases strictly decreases when this is the case. Also, fh1 is equal to 0 This implies fh of x strictly decreases from positive values to 0 when this is the case. Also, I can write fh of x strictly increases when x is greater than 1. fh of 1 is equal to 0. This implies fh of x strictly increases from 0 to positive values when x is greater than 1. So first we see that fh of x strictly decreases from positive values to 0 when when x is between 0 and 1, and then I see that it strictly increases from 0 to positive values when x is greater than 1. At x is equal to 1, the function takes on the value 0. That just means that the function is greater than 0 for all x greater than 0. Because if this is the case, the function is decreasing from positive values to 0. When this is the case, the function is increasing from 0 to positive values. That means fh of x is greater than 0 for all x greater than 0, except at x is equal to 1, because at x is equal to 1, fh of x is 0. fh of 1 is 0. That means now I can write what fh of x is. It is equal to this. fh of x, I can write that as g of x, gh of x minus ln x. This is greater than 0 for all x greater than 0, x not equal to 1. And that just means instead of gh of x, I can write, okay, so I can write gh of x is greater than ln x for all x greater than 0, x not equal to 1. That means I can write gh of x equal to, I know what gh of x is. It is this. So I can write x raised to the power h minus 1 by h greater than ln of x, greater than ln x for all x greater than 0, x not equal to 1. And that just means that gh of x, it tends to ln x. I mean, from this I can see that it is more than ln of x. It is more than ln x for all x greater than 0, x not equal to 1. And it tends to ln x as h tends to 0. And this I can see from the figure. It tends to, I'll just show the figure, it tends to ln x as h tends to 0. we have to keep this in mind that here I can see that ln x is bounded above by the function gh of x for all h greater than 0. So if I take a look at this diagram, I can see here that this is ln x and the function y, which is given this, and this. Here y is equal to x raised to the power h minus 1 by h, which is nothing but gh of x. So I can see that gh of x, it tends to ln x as h tends to 0. Gh of x, it tends to ln x as h tends to 0.